guys, we're doing target 1.1 day 1. It's a lot of ones. Our target, oh, and this is wrong. Stop Felix here. He's making it very difficult to write right now. Target 1.2. Sorry, this should actually say target 1.2. And again, that's just because that's the section from the book. We're skipping the 1.1 section. Stop hitting my arm. Thank you. Okay, so again, this is target 1.2 actually. But I'm going to tell you, I am at home right now making this video for you guys. The writing's going to be a little rough. My stylus for some reason keeps going out. As you saw me trying to write that too. So we're going to do the best we can. So what we're going to learn today in this video is I can determine if a relationship is a function. I can identify the domain and range of a function graphically. I can identify the domain of a function algebraically, and I can determine if a function is continuous. Okay. Okay. So what is a function? A function from a set D to a set R is a rule that assigns a unique element in R to each element of D. And that word unique is very important. Okay, so each element has to be unique. In the set D of all the inputs is the domain, and the set R of all the outputs is the range. Okay, so we're going to look at example 1. And example 1 is showing us, I forgot to put RD. You wait, stop it. Sorry. We should have a D and an R over it. So that circle is our domain, and that circle is our range. Okay. So like our domain has a set of like a bunch of different X's, and our range has a set of a bunch of different Y's. If you look at example 1, x1 goes to y, or A, x1 goes to y2, x2 goes to y1, x3 goes to y3, and x4 goes to y3. So a lot of students look at this one and go, oh wait, both of these are going to the same thing. That doesn't matter. Your two x values can go to the same y value. The opposite doesn't work. One x value can't go to two y values. So this is a function. This is like making me mad today, guys. This is a function because each one only goes to one place. If we look at B, right away, this x1 goes to y1 and goes to y2. I was gonna just like print this as our like written out notes instead of rewriting them. I don't think that's gonna work. So today's might be off, but from here on out, I will make sure I write them nicely for you guys. Again, this x1 goes to y1. I don't know why it's so bad. It wasn't this bad before. All of a sudden, like, stopped working. Whatever. Okay. So that's when you have like a map. So now we're going to look at when we have a graph. I feel like this is going to be like much more important. So we use what we call the vertical line test. And the vertical line test says, a graph in the xy plane defines y as a function of x if and only if no vertical line intersects the graph in more than one point. No matter where I choose to put a line, vertical, what just happened? It's freaking out, guys. No matter where I choose to put a vertical line, that I should be able to, I will only pass the graph once. And if it passes the graph once, then it's a function. So for example, if we look at this first one, I can put in a whole bunch of vertical lines. Each of them only pass through that parabola once. Okay? So I would say yes, this is a function. If I look at B, you only have to have one that doesn't work. Right? It passes, if I draw a vertical line right there, it passes through it twice. That is not a function. Same idea with C, right? No matter where I put a line, I could choose anywhere. All of these are only passing through that, this is a square root function. It's only passing through once. So that's a function. That's how you spell it. That's how you write an N. And then for this one, right, again, I only have to choose one spot. I could choose many of them, but I only have to find one that doesn't work. Okay? So that's pretty much it for functions. Not too hard. So let's look at our example 3. For example 3, we want to identify the domain and range graphically. This should be very familiar from last year. Okay? How I like to think of it is I like to think of it as a number line. Our domain is the x-axis number line and our range is the y-axis number line. Okay? So here, for our x-axis, there's nowhere on the x-axis I can't go. As this graph continues to go up, it's going to continue to go to the right. And as it continues to go down, it's going to continue to go to the left. So the domain, it's right in like green, I guess, is negative infinity to infinity. Okay. Our range, same idea, right? This graph goes all the way up. It has an arrow going all the way down. There's nowhere in the middle it can't be, right? If I went 4, oh, there's a point right here. Like, you can choose any number and find a point that has that y value. So our range, in this case, is also all real numbers, that negative infinity to infinity. Our domain first, again, with this number line. You see this point here, right? Nothing goes past that. So this number line is really, if I draw a straight line, going this way. Okay? And if you look at that 4, that's why I was talking about like the closed circles and the open circles. This is a great example of this is like a closed circle. We're on that 4. Okay? So my domain here would be, if I'm reading from like left to right, right, just like we were reading our number line, is it's everything less than or equal to 4. So if we put it in our interval notation, 4 is our biggest number, and we can be equal to it, and negative infinity is our smallest number. Okay, so our domain is going from negative infinity to 4. Now let's look at our range. Again, if we look, nothing's also under this point. Everything's above it. So we're going up this way, right? This is going to keep, while it's going this way, it's also like going up. So we're going to go up forever. And here, again, I'm on that point. I can be right here on my number line. Okay, so you kind of got to move the point over. Or if you want, you can look at it as being over here, right? I'm on that point and I'm going up from there. So my range, what's my smallest number? My smallest number is 0. Can I actually be 0? Yes. And then I'm going all the way up to infinity. Finally, our letter C, last one we're doing for domain and range here. Again, domain is across our x-axis. The one thing we have to be careful of is if you see both of these are going up here, and they're never actually going to touch this point, right? They're never actually going to touch each other. So they're missing this 0. Okay, so this is why we did intervals, right? Now, if knowing that, I'm at negative infinity, and then I'm going to 0. And then I have this other piece over here, which is 0 to infinity. Okay, so these are two unbounded intervals. And then we use this symbol here. It's just like a giant U, and it means union. Okay, so it's negative infinity to 0, unioned with 0 to infinity. And our range, same idea, but we're going, like, we have to think about our number line flipped 180 degrees, right? They are also never, these two things, they never actually reach this x-axis. So same idea, they're also never actually reaching this point, and they're going up from here. So our range, similar to this, but it's at 0 going to infinity, except I never actually reach 0, okay? So that's like the difference between the range between B and C. At B, I have a point where my y value is 0. It's right there, right? For C, I never have a point where my y value is actually 0. So it gets the parentheses. So that's identifying domain and range from a graph. We also want to be able to identify our domain and range from just a function, so algebraically. And there's two rules when we're identifying our domain and range. My dog is just like asleep on my leg. The first rule is that you can't divide by 0. And the second rule is that you can't square root a negative number. So we'll kind of see both of those in action. So looking at example 4a, I can't divide by 0. So here, 2 divided by x squared minus 3x minus 4, this cannot be 0. Okay, so x squared minus 3x minus 4 cannot be 0. Okay. However, solving this is exactly like what we did yesterday. Solving something that's not equal to 0 is solving something the exact same as solving something that is equal to 0. So I'm just going to factor. I'm going to pretend there's a 1 in front, right? So we get 1 times negative 4 equals negative 4. And we're adding to negative 3, okay? My two numbers that multiply to negative 4 and add to negative 3 are, nicely enough, negative 4 and 1. Since we multiplied by 1, we divide by 1. Negative 4 and 1. Okay? So we get x minus 4 and x plus 1 does not equal 0. Okay, so that's the only difference, is that now we're saying they're not equal to 0. We'll split them just like we did before. X minus 4 does not equal 0. Add 4. X does not equal 4. Okay, same thing with this side. X plus 1 does not equal 0. Subtract 1. X does not equal negative 1. Okay. So we're going to use this to help us find our domain. I'm going to write my number line. Okay, that's like our x-axis. That's an arrow. And what do we know? The two numbers that are important are 4 and -1. X does not equal 4. So anywhere time it does not equal it, there's a big open circle there. Right? Does not equal 4. It does not equal -1. Another big open circle. I have no other rules, so I'm just to say everything else is fine. So then our domain for this is going to be, well, again, you can think about negative infinity, infinity here. So I can start at negative infinity. I'm going until -1. It's open. Then I have to start right back at -1, right? The only thing that's not in it is -1, okay? But again, I can get as close as I want to -1 on this side and go to 4. And union that with. And then again, I start at 4 and go to negative infinity. Move this over. That is our domain there. Okay, so again, there's like 3 different chunks that we highlighted yellow, so you have 3 different chunks of your domain. Okay, B. This is the rule. I have a square root. And what did we learn up here? You can't square root a negative number, right? You can't do like the square root of -5, -6, whatever, right? So what that tells us is anything under a square root has to be greater than or equal to 0. It doesn't have to just be greater than 0. It can be equal to 0. You can take the square root of 0, but it can't be negative. So anything under a square root is greater than or equal to 0. Okay. So then again, I'm just going to get x by itself. So x is greater than or equal to -5. So now this is just like what we did yesterday. When I draw my number line, the only number I have on it is -5. It's greater than or equal to. I can be 5. I'm gonna shade that in. That's a closed circle. And then I'm greater than that. I'm bigger. Okay. So my domain is I start at 5, and again, that's a bracket because of the closed circle, and then I'm going to infinity. Look at us using all of these prerequisites we did over the past day or so. Okay, last example for finding domain algebraically. You can like combine all of these things. So first, I see this, right? It's under a square root, so I have x minus 3 has to be greater than or equal to 0. I'm going to add 3. So x has to be greater than or equal to 3. Next, I see this. Can't divide by 0. So x squared minus 4x can't equal 0. For this x squared minus 4x, if you look, they both have an x in them. That x goes on the outside. So x times x minus 4 does not equal 0. Split these up. X does not equal 0. That's already solved anywhere. That's already solved because it's already equal to 0. And then we have x minus 4 does not equal 0. And we add 4. So x does not equal 4. Okay, I need to put all of these things in a number line. I always start with the not equals. So 0 is important. And I can't be that, so I'm going to put a big circle. 4 is important. And I can't be that. And 3 is important from here, right? Now what's to write? Okay, hold on. And 3 is important. And since x is greater than or equal to 3, I can be that. Okay, now I can't shade in the whole thing because this specific tells me x is only greater than or equal to 3. So I can only go bigger. So I'm going to go here and here. Okay, so sometimes what happens here, as you see, is I know it can't be 0, but that 0 actually isn't that important because it can't be 0 anyway. 0 is not greater than or equal to 3. So sometimes like multiple things like make it not work. So for our domain, what's shaded, right? We start at 3, and I can be 3, and I go to 4. And then union, I go from 4 to infinity. Okay, so it's like these two chunks. So I have 2 chunks in my domain. Okay, the last thing we're going to look at is this idea of continuity. And continuity, a graph is continuous. We call it continuous. If I could draw it without lifting up your pencil. It has a lot to do with domain. Let's look at the things we just looked at here, right? Look at example A. Do you see how we had like 3 different chunks? I couldn't have possibly drawn this without lifting up that highlighter, right? I had to lift it up at -1 and lift it up at 4. So that one's not continuous. That's pretty much the basic idea. Same with B, however, right? I put my pen down here, my highlighter, and was able to draw the whole thing without lifting it up. There's only 1 chunk. It's continuous. I can draw the whole thing in 1 chunk. C is not continuous, right? I have 2 chunks. So from 3 to 4 and then 4 to infinity. So that one is not continuous. Okay. We can look at our graphs as well for this idea. And we kind of will look at some more graphs, right? If I look at A and A here, right, I can draw this and never have to lift up my pencil. I can draw this one and never have to lift up my pencil. This one, not so good. I have to lift it up in the middle. Okay, so C here is the only one that's not continuous. Okay, so it really does connect to this idea of domain, where if your domain is in pieces, then it's not continuous. If your domain is just one solid piece, it's continuous. So the only thing we're adding to it is types of continuity, so that we can label them. So the first type of continuity we have is a removable continuity, and your removable discontinuity. That's the same as like a hole. So if you remember from rational functions last year, we had these like holes in the middle of our graph. So a hole occurs when there's a common factor in the numerator and the denominator. Okay, so if you have to like cancel out a factor from both the numerator and the denominator, that's a hole. We call it a removable discontinuity. There are 2 types of non-removable discontinuity. Only one we're really going to look at. The one we're going to look at is infinite discontinuity. That's the same as a vertical asymptote. So that's like that problem C up above, right? Where if it hits an asymptote, That's an infinite discontinuity. That occurs when there's a factor in just the denominator. And then a jump, it occurs with piecewise functions that we're not really going to look at that much, but just know if your graph like randomly jumps, then it's also discontinuous. Okay, so let's look at example 5. It just shows some like pictures of what these things are. So here's our first one's continuous at all x. You can see that it's, I could draw the whole thing again without lifting up my pencil, right? Here, this is a removable discontinuity. This is like what a hole looks like. And then I have to lift it up, and then I can continue drawing. So right here is where I have to like lift up that pencil. This is the same idea. It is also a hole. These two are just showing you that it's called removable because I can technically put a point there somewhere else and say like, oh, look, I fixed it. And so that's why we call it like a removable discontinuity. That's not the biggest deal though, just the name. And then we have our jump discontinuity, right? Again, I have to make a big jump up for that. And then infinite, right? We've seen our vertical asymptotes before, right? We get closer to them, but never actually touch them. And so they make it so we have like two pieces of the graph. Okay, we're gonna look at some examples, just two, of finding these things algebraically. So you have x plus 3 over x minus 2. There's nothing I can factor here. And so I do have a factor in the denominator. And again, that x minus 2 cannot equal 0. So I'm going to add 2 to both sides. X cannot equal 2. Okay? This is an asymptote, right? If it's just still off in the denominator, it's a vertical asymptote or that infinite discontinuity. So how I would answer this question is there is an infinite discontinuity I would say at x equals 2. Okay? So there's infinite discontinuity at x equals 2. Let's look at b. b also has something that we're dividing by. So we know that can't be 0. But again, we always want to check to see if there's something that's the same in the numerator and the denominator. So I can factor my numerator. So I'm just going to do that like off to the side. X squared minus 4. This is a difference of squares. So I get x plus 2, x minus 2. Okay. So this function is actually x plus 2, x minus 2, over x minus 2. This is another reason why we call it a removable discontinuity, right? If I look here, these cancel, and I'm left with x plus 2. Okay, but we have to take that canceled one and say this still can't be 0. And add 2 to both sides. X. And then just saying this is a removable discontinuity at x equals 2. So finding your domain and finding discontinuities are very similar. For continuity, we just like name them a little bit more. So make sure you know the difference between like a whole versus an asymptote. All right, that's it.